This webinar is sponsored by NEC Corporation, a $37 billion technology leader with a 100-year history of innovation. NEC's Programmable Flow Networking Suite was the first data center-grade SDN leveraging the OpenFlow protocol. Deployed globally today, Programmable Flow transforms network performance and agility by providing production-ready SDN solutions that increase flexibility, visibility, and efficiency while reducing complexity and costs.
To find additional SDN, OpenFlow, and network function virtualization resources, visit ipspace.net/SDN. As you remember, every networking device we use today usually has three planes. The data plane, where the actual forwarding is done, and this is where the ASICs are sitting or whatever other silicon you're using to quickly forward the traffic from input interface to the output interface. The forwarding table has to be programmed, and it's usually programmed through the control plane, which is where various protocols like OSPF, BGP, and so on are sitting. They exchange information with the neighbors, they figure out the topology of the network, they figure out what the best path to a certain destination would be, and then they install that information in the IP routing table. The best information from the IP routing table goes into the forwarding table. On top of everything else, we have the management or the policy plane, where we do the configuration, and we can use CLI, GUI, API, it doesn't matter, to monitor the device, to see the parameters of the device, and to adjust the operation of the control plane protocols. In an OpenFlow-based network, there is a physical separation between the control and the forwarding plane. The basic principle is that the control and the management plane are in a dedicated controller, and the networking devices just perform the forwarding and the maintenance functions. Of course, you have to configure the networking devices somehow. They need an IP address because OpenFlow runs over TCP. Then you have to configure who the OpenFlow controller is. Then these devices would establish an OpenFlow session with the controller. As soon as the OpenFlow sessions with the controller are established, the controller would run Topology Discovery, and later on I'll show you how that's done, and build a model of the network. This is almost identical, for example, to how OSPF works, only you have the topology in one centralized place. It's not in every single forwarding entity. Then, for example, when you configure or the OpenFlow controller discovers that there is prefix B here on the right-hand side, the controller would enter that information in the network topology model, and based on the topology and the connectivity information, like prefix B is here on the right-hand side, it would compute the forwarding entries that need to be downloaded in every single device, and then it would download those forwarding entries, and the end result would be almost identical to what a routing protocol would give you. Obviously, if we just emulate routing protocols, we haven't done anything. We should be doing something better. When ONF started promoting OpenFlow, OpenFlow was in version 1.0. Very quickly, people discovered that it's missing a number of things. So in version 1.1, they added MPLS, multiple tables, so you can do multiple forwarding operations in sequence like real-life switches do. In version 1.2, they added IPv6 as well as an extensible matching setting mechanism that allows you to match on almost anything. In 1.3, they introduced support for provider backbone bridging, but more importantly, 1.3 contains metering on individual flows. So you can implement counters on individual flows and report what individual flows are doing. And then 1.4 has flow monitoring, flow eviction, transactions, and so on and so on. So you see, OpenFlow is progressing nicely from an initial proof of concept to a really usable protocol. most hardware vendors implemented OpenFlow 1.0. Most implementations you've heard about in the last 2 years or so were OpenFlow 1.0. I'm not aware of any major vendor implementing OpenFlow 1.1 or 1.2 because there's a major gap between 1.0 and 1.1. It introduces new message format and multiple tables and so on and so on. And the development of the standard was going so fast that everyone went like, hey, wait. We're not going that fast. We don't have the resources to develop all these new versions of this protocol. We'll wait. And as OpenFlow slowly stabilized around version 1.3, vendors started implementing it. And NEC was the first one to come out with a major OpenFlow 1.3 compatible product. And since then, I think at least one other vendor also launched OpenFlow 1.3 support in their switches. Like any protocol, OpenFlow has a number of different message types. You can configure something on a switch. You can ask the switch what features it supports. Then, most importantly, you can modify the forwarding entry. You can read the statistics. There are barriers which are sort of similar to transactions. And then to support control plane protocols and processing of unknown traffic, there's the capability to send a packet to the controller and the capability to send a packet from the controller and out through a physical port into the network. We'll see in a few slides how that's used. When people talk about OpenFlow, they very commonly think that a flow is what other people would call a microflow, a full 5-tuple with source, destination addresses, and port numbers. Early implementations of OpenFlow controllers actually installed microflows into the hardware. And that doesn't work because the hardware is not big enough usually to support that concept. Remember that a forwarding entry is something that matches something. And that something doesn't have to be a single session flow. So what can it be? It can be any combination of a number of usual packet header fields on layer 2 or layer 3. So we can match MAC addresses. We can match on destination MAC or on source MAC or on both, and OpenFlow 1.1 gives us wildcards. We can match on VLANs. We can match on MPLS tags with OpenFlow 1.1. We can match on provider backbone bridging headers, including SIDs in OpenFlow 1.3. IPv4 addresses were always there to match, and wildcarding was always there. And we can also match on ARP fields and DSCP bits. With OpenFlow 1.2, we can match on IPv6 addresses, and with OpenFlow 1.3, we can match on the extension headers. Then we can also match on layer 4 protocols and TCP and UDP port numbers, and with extensible matching, we can match almost anything with OpenFlow 1.2. Remember that even though the protocol says that you can match all of this, it doesn't mean that your idea will actually work on an actual switch. If the switch doesn't have IPv6 support in hardware, it will be very hard to match on IPv6 addresses. Some switch vendors might decide to just bark back and saying, well, we don't support that. Other switch vendors might accept the flow entry and implement it in software, which means that you will have like several orders of magnitude lower performance than you would have in hardware. Also, very simple requirements like forwarding on destination MAC address or forwarding on destination IPv4 address can be implemented in the large tables that the switches have. Almost everything else, like matching on port numbers or matching on source and destination address, almost any other combination of matching fields requires better hardware with better matching capabilities, and that hardware is usually called TCAM and is the same hardware that's used for access control lists and policy-based routing. Now you know that the number of entries in an access control list on almost any switch is severely limited. And this is the same hardware that's used for OpenFlow entries. So don't expect more than a few thousand OpenFlow entries on a regular switch that wasn't designed particularly for flow-based forwarding or for OpenFlow like NEC's programmable switches were. If you're lucky, if the switch vendor was smart in their OpenFlow implementation, you might get simple entries installed in hardware tables, but then you might get a situation where a vendor would support layer 3 forwarding based on destination IPv4 addresses in hardware and layer 2 forwarding based on MAC addresses only in software. I don't understand why anyone would implement things that way, but I've seen it implemented, so be careful. Once you have found and matched the flow, you can do all sorts of actions on the flow. Usually, you would send the traffic to an output port. Or, before sending the traffic, you could push or pop VLAN tag or MPLS tag, or you can add provider backbone bridging header to it. In theory, you can do header rewrites. So you can rewrite the MAC header for proper layer 3 forwarding. You can rewrite layer 3 and layer 4 information to implement NAT or server load balancing. But don't expect these actions to be either implemented or implemented in hardware. The more complex the actions are, the more probable they are implemented in software, and therefore they are slow. Then there are two special actions that are extremely useful. The first one is send to normal processing. So instead of re-implementing every switch functionality from scratch, you just add OpenFlow on top of the regular switching behavior and tell the switch, you know what? For example, I'll implement packet filters, and whatever I match with the packet filters, I'll just drop into normal processing. And if you don't know what to do with a packet, the switch can always send the packet to the controller. This is, for example, how you implement topology discovery in OpenFlow. As the devices connect to the controller starts building the network topology model. Initially, it knows that devices are there, but it has no idea how they are connected. First thing the controller has to do is it has to figure out where the interfaces are. So it has to send an interface discovery OpenFlow message to the switch, asking the switch about OpenFlow enabled interfaces. And it gets a list of interfaces back. So now it knows that this switch has two interfaces. It still doesn't know where the interfaces are connected. In traditional networks, we would be using OSPF hellos or LLDP packets or anything functionally equivalent to figure out who our neighbors are. And guess what? Most OpenFlow controllers on the market are doing exactly the same. And many of them are actually using LLDP packets. But now, how can a controller send a packet through a switch port? You do remember the packet out message, right? A message by which the controller tells the switch to send this particular payload as a regular packet through one of the ports. And if the payload is an LLDP packet, that packet will get sent across the link. The other OpenFlow switch on the other end receives that packet, and because it's an OpenFlow switch, it doesn't have LLDP in its control plane, so it's totally clueless. It doesn't know what to do with the packet. So what it does is it sends the packet to the controller, and so the controller now receives a packet in from the bottom switch saying, I received this packet through my top port. And the LLDP content says, well, this packet is coming from the top switch going through the bottom port. So now the controller can connect the two ports in the network topology and install that link between the two ports. As this is repeated across the whole network, the controller builds the topology of the network. And later on, when it has to monitor the link state to detect link failures that are not reported through layer 1, it has to use a similar mechanism. Which brings me to the following thing. Do keep in mind that OpenFlow is not really a new concept. We were doing similar things in the past, in frame relay, in ATM, in Sonnet or SDH, depending on which continent you're on. All these things were managed, configured through the central controller. And what those controllers were doing were actually downloading forwarding tables. Only they would have input and output DLCI or VC-VP pairs into the forwarding hardware, which was in the actual frame relay or ATM switches. OpenFlow is really nothing new. Whenever we have an architecture that's similar to the past architectures, we should keep in mind what problems we had with those past architectures. The first problem was scalability, which triggered the forwarding state abstraction, which brought us MPLS. Second problem is, how do you have network resilience with centralized control plane? In SDH, for example, they solved that by pre-configuring backup paths so that the SDH boxes could flip over to the backup path without the controller. Then there's the question of, how do I handle fast feedback loops and fast convergence? And finally, there's the question of, how do I detect link failure that doesn't result in layer 1 interface failure? In almost any technology, we had in the end some node-to-node signaling that was used to detect data plane failure or transmitting hardware failure. And all these things will have to be reinvented in OpenFlow. The important difference between, for example, Forces or MPLS-TP and OpenFlow is, on the other hand, that this time there is real customer pressure. So this time it's customers asking for OpenFlow and not vendors or IETF workgroup members dreaming about something like Forces, which was never implemented by any major vendor. Of course, eventually people get carried away. We are hearing claims like, well, OpenFlow will obsolete all the networking protocols. We don't need any protocols anymore because now everything is running in a controller. Whoever is making those claims will be quick to give you a long list of why routing protocols don't work. They are loosely coupled, they're destination only, they don't know about loads, so some links could be overloaded and some could be underutilized. You get micro forwarding loops due to eventual consistency, and you can't forward based on source addresses. By the way, there's a good reason for that because it just wouldn't scale. But let's forget that. So these are the usual problems one would tell you are there. On the other hand, there are a few features of routing protocols that make them useful. They have been proven. They are reliable. They are deterministic. They are self-healing. They scale. After all, the whole internet is running on BGP. So if you want to implement something that mimics the routing protocols, then an OpenFlow controller must reinvent all the wheels. There will be some scalability problems. There will be some auto-discovery problems. There will be the problem of fast convergence and fast control loops and so on and so on. And on top of reinventing all these wheels, it has to provide some added value. So far, I've seen only one OpenFlow controller, and this is NEC's programmable flow, which has implemented most of these wheels. They've been working on this for years, and if you want to know more, do go and listen to the OpenFlow Scalability Challenges part of the SDN Use Cases webinar, where I explain all the different mechanisms that programmable flow is using to scale, to do fast reroute, to survive a little bit without a control plane, and so on and so on. But in most cases, I wouldn't focus on replacing routing protocols. It's better to focus on new edge functionality. Which brings me to, how can we use OpenFlow today? Well, you can use it natively. As I said, NEC did a great job with programmable flow. They have implemented more or less all you need to have a reliable OpenFlow-based data center fabric, and I haven't seen any other product where I would as comfortably say, yes, this would work in a large-scale data center environment. On the other hand, if you just focus on the edge, if you're saying, okay, I will ignore the uplinks work as normally, and I will focus on the edge ports and, for example, implement security features there. Or if you say, well, I will use overlay networks and I will implement OpenFlow just for VM to VM connectivity, then your life becomes way simpler. Because if you want to implement a fabric, then you have a number of tightly coupled elements that interact with each other, and that's hard. If you focus on edge only, then you can have many elements and they are totally decoupled because you're not using a controller to control the uplinks, and the problem becomes way more manageable. Then, of course, there are all sorts of things that we need that are still not covered or are not covered well with OpenFlow. QoS, for example, or line card protocols like LDP or LACP or BFD. Many vendors are implementing this, and then they have their own vendor-specific extensions to OpenFlow that allow the controller to use this functionality, which obviously is problematic because then the controller vendors have to code to particular switch vendor, and it brings you the interesting problem of testing and release dependency and so on and so on. Some academics are using OpenFlow in so-called ships in the night model. They are using OpenFlow in parallel with traditional forwarding. So, for example, you enable OpenFlow on some ports or only on some VLANs, or you use OpenFlow to classify the traffic and then you drop it into normal processing. So you don't have to reinvent all the wheels because the wheels are still turning in the traditional switching mode. Or Juniper had a really interesting concept, I don't know how far they got with it, to use OpenFlow classifiers as part of the regular packet processing. So they would combine OpenFlow entries with the IP routing table and treat OpenFlow like an additional routing protocol with a different administrative distance. In their case, OpenFlow would provide sort of temporary configuration for certain forwarding flows, which is great because if you really go and modify the switch configuration and then someone saves it, it's there forever. It doesn't just disappear. Regardless of the state of the controller market, there are loads of companies that already have shipping OpenFlow products. I will not go into who they are. They are here on the slide for reference purposes only. On the controller side, the only controller that I've seen so far that actually solves the whole end-to-end fabric forwarding problem is NEC's Programmable Flow Controller. VMware NSX is a great controller, but it works only on the edges, so they decided to ignore the core, which was probably a good decision because it totally simplified their life and made their controller way more scalable because they don't have to deal with tightly coupled elements. I don't know how far Big Switch Networks got. I still haven't found any documentation on their website. Cisco has shipped extensible network controller and HP has shipped WAN SDN controller. They are both shipping. Documentation is on their website, and it looks like they are both treating their controller as a platform on which to write additional applications. They both have some very simple applications. We'll see how that evolves. On the open source front, you just pick your programming language. There will be a controller written in that language. Obviously, the most popular one or the most talked about one these days is Open Daylight, and we are waiting for the first public release to ship. If you want to know more about OpenFlow and SDN and the dirty details, there is a whole OpenFlow and SDN webinar available on my website. It's public, so you can just download it and listen to it. The first question is, can multiple actions be defined for a single rule or are rules chained? For example, can a single rule trigger rewrite header, add MPLS label output to this port, and so on and so on? Absolutely. For every flow matching entry, you can have multiple actions where actions can do whatever the switch hardware supports. And for switches that support multiple tables, which means that they have to talk OpenFlow 1.1 at least, the actions accumulate as the packet goes through different forwarding tables. So in one forwarding table, you may set the VLAN. In the second forwarding table, you may set the DSCP bits. In the third forwarding table, you may set the MPLS label. And in the fourth forwarding table, you figure out what the output port is and send the packet to the proper output port. So yes, you can do that. Next question, can you use the output action to output to multiple ports? Absolutely. You can use multiple output to port actions to, for example, do packet flooding or packet replication or span type functionality. Next question, it looks like controllers are mostly data center local. So are commercially released controller suites functioning as islands from the management point of view or hierarchical with a single management interface? Right now, most commercial controllers are what you would call an island when we talk about OpenFlow controllers. They do have northbound APIs, so you could implement an umbrella system that would configure all the individual controllers with the same characteristics, for example. We will definitely need something beyond that, be it a confederation of controllers or hierarchical mechanism. On SDN controllers using more traditional mechanisms, for example, Juniper Contrail or Nuage VSP or something, they're both using traditional BGP protocol with VPN v4 address family to exchange reachability information between controllers in a federation. Their implementation is actually no different from a very large PE router when looked at from the outside. Next question, end-to-end QoS in packet networks has always been difficult. How can OpenFlow help? That's one of the open questions. There's not much QoS support in standard OpenFlow. You do have the capability to match on DSCP bits, and you do have the capability to set the DSCP bits. You can also match, as you know, on any information like port number, for example. Queuing still can't be configured through OpenFlow, whereas policing can be. So flow meters can already be configured through OpenFlow. So you can monitor the traffic, you can police the traffic through flow meters, you can mark the traffic, and you can then match on the markings. And if you have pre-configured QoS in your switches through some other means, then the switches can do queuing based on that marking. You know that QoS is a hard problem. I haven't seen a controller that would do something really fancy with QoS. NEC's programmable flow controller can do a lot of things, but I don't think I've seen load-based balancing, for example. But of course, it can do the more traditional things like matching on DSCP bits and selecting different paths and so on and so on.
Thank you for attending this webinar sponsored by NEC Corporation. For more information on NEC or the Programmable Flow Networking Suite, visit us online at necam.com/SDN. To arrange a demo or to pilot Programmable Flow SDN, call your NEC account rep or contact NEC directly at necam.com/contact us. Thank you for your interest in NEC's Programmable Flow Networking Suite.
Additional SDN OpenFlow and network function virtualization webinars, recordings, and workshops, as well as other resources like books and case studies, are waiting for you at ipspace.net/SDN.